there, my name is Alexey, and today I'm going to talk about optimization of servers for high throughput and low latency. First, let's start with a couple of words about me. I'm a performance engineer at Dapper Labs. Previously, I was working on traffic, networking, databases at Dropbox. I have background in hardware optimization, OS optimization, application optimization, real user metrics, so all over the place. So before we start, let's get it out of the way. Disclaimer. First of all, the biggest performance gains you can have are on application level, in its business logic, in things around it like load balancing, in data structures, algorithms. And what's nice about the stuff we're going to talk today is that you can apply it to pretty much any application without changing usually a single line of code. But it can give you like 10% improvement or 20%, 100% improvement. When we talk about optimizing the application itself and its business logic, we are talking about orders of magnitude improvement. A couple of examples of the things we did in our production system. So like optimizing the load balancing algorithm gave us hundreds of milliseconds of better response time. Getting that on lower levels is pretty much impossible. Or we did work asynchronously out of hot paths, like pre-compressing assets for our website. Again, like no amount of optimization on the lower levels could give us that kind of performance improvement. Or switching from zlib to broadly on data storage side. Again, free CPU by changing the business logic and lots of storage space win. Same with switching from B+3 storage engine to LSM based storage engine. Again, lots of compression improvements, lots of reduce database size, etc. So focus on your application first, and lower levels are fun. They are rewarding when they are bottlenecks. So if you have packet loss on your network, of course, like optimizing anything in your application won't help you much. But at the same time, lower level optimizations are only meaningful where they are bottlenecks or you want to get every piece of performance out of your application. So with that out of the way, let's jump in. We'll start with hardware. So on the hardware layer, we're gonna start with CPU. So CPU and memory. Here, what you want to have is the newest CPU. Not exactly the fastest in terms of gigahertz, not the biggest in terms of cores. What you want to have is whether you are picking your hardware yourself or you picking the instance in Amazon or Google or Azure or whatever. You want to pick the newest CPU because it will have the most hardware offloads, it will give you the most flexibility later when we discuss like the higher levels. So the newest possible CPU with the most possible offloads you can get. And offloads are actually game changer because some of the things that were not possible without offloads are now possible. Things like encryption everywhere. Encryption with ASNI is pretty much free. MTLS and certificate verifications. They were very hard previously. Now with AVX to ADX, they are getting easier and easier on the hardware. It's not free yet, but it's getting there. Or hashing. People used insecure SHA-1 and MD5 hashes for performance purposes still. Again, these can be switched to SHA with new SHA-NI instruction set. So focus on the newest possible CPUs. Once you picked a newest possible CPU, you need to see what configuration you want to have. And for low latency, what you want to have is as few NUMA nodes as possible. Try getting a single NUMA node if possible. You want bigger caches, you want disabled SMT, you want more gigahertz, you want more memory channels so you are not blocked on data. For high throughput, you probably want the reverse. You have more cores, even if they are slower. You want to have more memory, so that you can fit more instances processing the data in parallel. You want to have SMT for more CPUs, even though they are logical ones. Speaking about measuring the CPU load, it gets a bit trickier. So when you usually look at CPU busy, that doesn't mean the CPU is actually doing useful work. Maybe it's just waiting for data. There are a couple of methodologies that allows you to drill deep into the CPU pipeline layer by layer and discover where the actual bottleneck is. Long story short, the CPU pipeline is just a pipeline at the end of which you have instructions, retiring or not retiring. If they're retiring, that's good. If they are not retiring, the CPU is stalled. Then on the next layer, you can divide retiring instruction into actually useful instructions, or bad speculation. Stalls you can divide into front end and back end. Then you can go one layer deeper, one layer deeper, one layer deeper. The newer the CPU, the lower you can get in that stack, up to the point where you can discover whether you are L1 bound or maybe DRAM bound. If you are DRAM bound, is it the memory bandwidth or memory latency, etc. So that kind of top-down analysis allows you to drill deep into your workload and understand where are the bottlenecks. That thing would allow you to either pick the hardware and make either physical hardware if you design one, or the cloud hardware if you pick in between different instances. Now you can have a meaningful understanding of, okay, if I increase my DRAM bandwidth, I will get X performance win. If I get more cores, I will get Y performance win. And then you can compare without running your software on each and every possible hardware class out there. So all of that sounds complicated, but there are tools for that. All of that is codified. You can try PMU tools, which have top level performance analysis codified. So here is an example of running an application with just first level of TMA, which will show you whether it's front-end bound or back-end bound. Here is the same example with level 3. So level 3 will show you that it is actually core bound by 45%, and at the same time it's memory bound by L1 bound specifically for 32%. That is, of course, a very, very unoptimized application, and it can not only show you what kind of hardware you want to have for that application, but also, for example, for that one, more ports would be useful. But it can also show you, okay, your application can be optimized on algorithmic side, so it utilizes L1 properly. Now let's switch to slightly different network cards. So when picking network cards, in the cloud, you usually don't care. They already have pretty good cards because they need to slice them up and divide between users. If you pick in your own network card, just pick 25G or above. Anything beyond that will have hardware limitations. You don't want to have these. Also focus on the open source drivers, very small firmwares, active community. Again, if you will use things like XDP, active community is very important. Last but not the least is PSI. So pressure stall information allows you to get bottlenecks of your specific application, whether it's blocked on memory allocations, on CPU, or on I/O. Additional beauty of it is that it is available on per-cgroup basis, which means you can ask whether your container would benefit from more IOPS, or maybe your container would benefit from more CPU. So please enable it. If it's not, use it. If you are not using it, just take a glance and probably it will give you some more insight into your production system and maybe misplaced limits on your Kubernetes containers. If you want to look deeper into how hardware works and how software interacts with that hardware, I highly recommend you Understanding Software Dynamics book. It is quite good, especially its hardware, software-oriented chapters. Let's switch gears to Linux kernel and its optimizations. So first of all, the biggest optimization you can have is to just update your kernel. Each time we update kernel on production system, we see random performance improvements in areas we did not expect. So please do that. It's always great to have a new kernel. If you're still on 4 point something, please upgrade 6.0 will come out soon. So it's clearly a signal. Don't use 4 something. Now let's talk about CPU and memory. So now that you have your fancy CPU, it's time to put it to good use. If you constantly utilizing that, set a governor to performance. If you are not, then ShadUtil or PowerSave are your friend. They will save you a lot on energy bill. Also, utilize Intel P-State or AMD P-State. AMD P-State was released recently. It's available in new Linux versions, so please use it. It's way more efficient. If you have multiple NUMA nodes, then you want to set up NUMA affinities properly. You don't want to spread your application across multiple NUMA nodes. Probably if you have a scheduler, you want to teach it how to properly affinitize the software it is running. Also, many of old tuning guides actually advise to disable transparent huge pages. So you want to leave them enabled, at least in M-advice mode. Most of the allocators nowadays can actually utilize transparent huge pages, set these M-advices without affecting any other hardware software on the box. So please don't disable transparent huge pages unless you have a clear evidence that they are hurting you. Leave them in M-advice mode. Networking, my favorite subject. I could talk days about it, but we don't have days, we have 20 minutes. So the gist of the idea is the following. First, you want to check that your limits are set up correctly. Your buffer sizes are big enough so you don't drop the data on the floor. Check the network card stats to see if there are any overruns, drops, misses, errors, whatever. If these are present, no amount of subsequent optimization would likely help. So check these first. Second, litmus test for good networking tuning is that your data processing is spread across all the cores equally. All the cores in the system should be handling interrupt, processing, TCP stack, running the application, and sending the data back out. The third thing you want to check is that the data does not jump between CPUs. So interrupt and stack processing is on the same CPU. Data is handled by application on the same CPU, and data gets out of the stack on the same CPU. Jumping between cores is very, very expensive. So try to minimize that. With these three, you're probably fine. There are scripts to help you with most of it. Mellanox and Intel cards have scripts to actually set all the affinity parameters. Linux has extensive docs for setting up the affinity so data does not jump between CPUs, etc. So please utilize these. One caveat though, for low latency systems, what you want to do is instead of spreading the data processing across all the cores in the system, you probably want to concentrate them on a single NUMA node. So whatever NUMA node is your network card connected to, use it to process the interrupts and run your application. So yeah, that's the only caveat for a multi-NUMA node low latency system. The next one is the transport layer optimizations, and here generally the good thing to do is to enable FQ scheduler because it has pacer. So pacing is a very neat thing that you always want to enable. FQ pacer is slightly better than the built-in TCP pacer. The second thing, speaking about TCP, you probably want to enable BBR if you're dealing with bulk traffic. For low latency, there are caveats. Also, if you have an ability, please try out BBR v2. That is available nowadays for Linux as a patch. And always, whatever you do with transport layer stack, verify that your tunings are actually beneficial. So whatever I'm saying, that may be true for my system, it won't be true for yours. So please verify by yourself. SS is your good friend here. So recent versions of SS can actually show you whether you are send window limited or receive window limited, and you don't ever want to be send window limited. That's probably a misconfiguration on your side. So please, for every tuning, try to do some basic sanity check on stats of TCP connections, whether bandwidth went up or down, whether retransmits increased, etc., etc., whether RTT increased. So please verify every tuning that you make with SS data. Sysctl cargo Calton. So no network representation that touches optimization can go around these. So here are some examples that actually work for us. Let's just deal with that. Slow start after idle is quite useless if you have FQ with spacing. TCP MTU probing is on the edge, is always good to kind of link the network layer and transport layer. So the RMEM, WMEM, again, we have enough memory on servers nowadays, so bumping these up is a good idea. And when you bump them up, you also want to set them not send lowet, to not spam the lower layers of the network with the data that hasn't been sent yet. So that's all for Sysctls that are generally useful. Please free to comment on that one. Maybe you had different experience with them. Now, speaking about the books I can recommend for that section, Systems Performance and BPF Performance tools are two that come to mind immediately. These will give you tools to discover things on your own. This is a 20-minute talk and I can't possibly put everything in. So please just use these books. They will show you all the possible ways you can introspect Linux kernel to get the data you want. And not only Linux kernel, you can actually introspect running applications on the fly. So to debug things like, why is my application blocking from time to time? Or why does my packets get dropped from time to time? Like where in the stack they are dropped, etc., etc. Like all these questions can be answered by a single bpftrace or BCC tools program. So please use these books, they are awesome. The meaty part, the application tuning, again, that can give you the most for your buck. First of all, as usual, upgrade your compilers, Toolchains, Runtimes, whatever it's called in your world, upgrade them all the time. For example, Go runtime upgrade can give you easily tens and hundreds of % of performance improvement just by bumping a version. If you compile your own software, then put in proper mtune and mark. Given that you've already picked a CPU, if you can have a lowest common denominator for your CPU, just put an mmark for it into your build scripts. It will give you free performance. Enabling LTO is also a good thing. Nowadays, most compilers can actually do profile guided optimizations based on perf data from production. So by collecting perf record data from production, you're not only adding introspection into the system, but you can feed back that introspection back into the application. So again, if you control your build pipeline and you have perf records, then just feed them back in. Free 10 to 20% improvement. If you're really brave, you can also do post-link optimization, and you can use Facebook Bolt project to optimize your compiled application even more, again, based on the performance data gathered from production. Libraries. Modern applications have thousands and thousands of them. Some of them will likely be in your hot path. So keeping them up to date is very, very important. If you have that fancy CPU of yours with all these instructions, and at the same time your library is 10 years old, it probably won't even know about them. So keep your libraries updated, security will be happy, performance will be happy, everyone will be happy. On a more specific note, malloc. Most C++ applications are at some point bottleneck on malloc, so it was trying out its replacement, gmalloc or tcmalloc. Try them out. You don't need to recompile anything, just LD preload them. Open up their tuning guides, tune it to the workload of your application, see whether it improves things. Another common example is OpenSSL. You can try out boring SSL and see if it helps. It's mostly a drop-in replacement. It has a couple of additional features like equal priority cipher groups, which would allow you to play with things like AES or Cha-Cha, depending on hardware, optimizations available, etc. Try playing with its configuration. Try switching from RSA to ECDSA if you control the environment. It would not remove the bottleneck on OpenSSL in some cases, but in some cases it will be a game changer. Another example is, for example, zlib. Zlib has a bunch of forks. You can try them out, like one from Cloudflare, another one from Intel. So see which one performs better in your environment. And again, if you have control over that environment, maybe it's just time to ditch the zlib as a whole and just use something modern like Broadly or zstandard. There is no need to actually deal with all that legacy zlib stuff. As for the books for that section, like optimizing application is quite a big task. So for internals, I would recommend the Designing Data-Intensive Applications. It's a quite good book that gets into the details of many different things. So reading it is a good time spent. The second one, surprisingly, is a SRE book with chapters on load balancing. Again, load balancing is a glue that connects different applications and can easily get you hundreds and hundreds of milliseconds, mainly for playing with the environment, not for the application itself, or maybe with some parts of application like queuing system, but another story. So load balancing chapters, overload chapters, and cascading failure chapters are generally a good read for that kind of glue that connects everything together. With all of that, thank you. Again, it was very dense. It's like 20 minutes for a relatively big subject, so hopefully at some point I will put that all into some kind of blog post that can be read in a more relaxed way. Anyway, thank you for listening again.